Yeah. Okay. So, good evening, everyone. On behalf of the IIChE student chapter slide, I welcome you all to the inaugural talk of the IIChE lecture series. Today, we are delighted to have Professor Chirodeep Bakli with us. Before I move further, let me give you a brief introduction about him. Currently, Professor Bakli is an assistant professor at the School of Energy Science and Engineering at IIT Kharagpur. He obtained his bachelor's degree in energy engineering in 2010 from IIT Kharagpur itself and was awarded the Institute Silver Medal for his outstanding academic performance in his department. He obtained his PhD in mechanical engineering in 2016 from IIT Kharagpur as well. Previously, he also held the position of an assistant professor at the Department of Mechanical Engineering at IIT Ropar, and his current research interests lie in the interface of microfluidics and nanofluidics, interfacial phenomena, electrohydrodynamics, molecular dynamics, renewable energy, thermal and fluid sciences, and building energy. So today, Professor Bakli will be delivering a very interesting talk on the duality of contact angle and wettability. So before we begin, just a couple of quick points. It would be great if everyone could turn on their videos so that we reach closer to an in-person talk, something which we have been missing out on for quite a long time. And also, if you have any questions, you can put them in the chat and the moderators would convey it to Professor Bakli at the appropriate time. Okay, so without further delay, I invite Professor Chirodeep Bakli to deliver the much awaited talk. I hope all of you will enjoy the same.
Thank you, Sanket. Thanks a lot for inviting me. So, yeah, as in IIT Ropar, it was mostly a BTech batch I used to interact with. So, you reminded me of that when you said most people won't be able to understand if I start giving a talk on interfacial phenomena. However, on that note, how is the composition? It is mostly second year, third year students, right?
Yeah, right.
Okay, great. So we would try to keep the talk as simple as possible, and from my side, all the participants are welcome to ask question at any point of time. We would try to make this as interactive as possible, the best we can do at the times of pandemic. So yeah, thank you everyone for turning up today. So without any delay, let us start with the presentation. Please tell me if you can see my PowerPoint presentation in full screen view.
Yeah, I can see it.
Okay, great. Thank you. So today's topic would be on the duality of weightability and contact angle. So to begin the topic, I would like to briefly explain the terms weightability and contact angle. However, after giving you a prelude, we would come back to these two terms. So the general notion, layman's concept of weightability is the degree to which a surface would get weighted by a fluid or water, most commonly, is termed as the weighting propensity or the weightability of the surface. And this weighting propensity is measured by something called the contact angle, which is the angle subtended by a fluid inside the fluid droplet itself on a surface. So you might have come across this terms several times, starting from middle school, where capillary rise, the meniscus, and all those discussions were put in your science textbook. So we would be visiting these concepts, but why these concepts are important from an engineering point of view, for that we need a short prelude. So this is something that we would follow. The talk is separated into 3 chunks, and before we start with each of these chunks, the tone of the slide would change to sepia, so that people would get a heads up that we are switching over. Okay, so let us begin with the prelude. So as you know, my background is fluid mechanics, so we would be talking about, and obviously contact angle and weightability are something that is related to fluids and fluid motion as such. So we would be dealing with something that is very common, that is motion of fluids through channels and pipes. So something that you see in your regular tap water in your kitchen or bathroom, or flow through any such conduit. So typically such flows. So please also let me know if you can see this scribbling.
Yeah, I can see it.
Okay, great. So typically such a flow is usually observed in a channel or a pipe of circular cross section, and imagine this to be circular. The stab is quite slippery, so sometimes the lines do not come properly. So mostly mechanical, chemical, or civil engineering fluid flow analysis would deal with flow through channels and pipes, and these channels might be parallel plate channels, pipes with circular cross sections, and in certain not so common cases, these might be flow through channels with rectangular or square cross sections. Now, the beauty of these flow situation is that the solution of the flow or the velocity profile can be obtained analytically. Hence, as engineers, mathematicians, scientists, we are very much interested in flow through channels and pipes. Pipes with circular cross sections, channels which are semi-infinite. That is, only one of these dimensions is finite, and in, let us say, if this is the direction, in x and y direction, the parallel plates, they run in infinite dimensions. So these flow problems are pretty much easy to solve, and since I expect most of you have done a basic fluid mechanics course, even if not, we try to solve a flow problem using conservation of momentum, which is very similar to Newton's second law, and that second law for a fluid in a control volume is given by a lot of mathematicians and scientists, one of them being Navier, and then for a particular Newtonian and Stokesian fluid, it is reduced to a very peculiar form, and that partial differential equation is known as the Navier-Stokes equation. So without going into that, the details of the partial differential equation, we try to do it for the most simple case. We do it for a case where this flow has come and it has evolved, and it is something like called a fully developed. So basically, again, avoiding the jargon, a fully developed flow is a flow which is not evolving as it travels along the x direction. So all the entrance effects have been removed, so the pipe or the channel is sufficiently long, and we have a flow which is no longer evolving as it travels down the axial direction. So for a fully developed flow, we try to solve the equation in this form. And we, fortunately for this, we have an analytical solution. So this is in Cartesian coordinates. For circular cross section, it can be in polar coordinates, and we try to solve this and obtain this equation. Now, obviously, some of you must be very much irritated by seeing a differential equation. So need not worry, this is just the beginning of it. We won't be doing any more differential equations for the rest of the lecture. But the point that I want to bring home is that this equation is a second order equation requiring two boundary conditions. So just by analyzing the geometry, we try to put one of the boundary conditions as the surfaces of the pipes or the tubes being solid, and a solid geometry would not allow a penetration across the surface. So no fluid would come out of this surface, hence making the velocity at the z direction at this point to be 0. So that gives the first boundary condition. The second boundary condition is also can also be intuitively structured from this from the geometry, is that we know this walls are solid and immobile. So a fluid volume staying next to the wall would be tending not to locomote, not to move, while the fluid volume that is towards the center would move. So using that analogy, we try to write it as if u is the velocity in x direction, so u at wall equal to 0 is the first boundary condition, and v, which is the velocity at z direction at wall, is 0. Using these two boundary conditions, we try to solve this equation. So while the second boundary condition is called the no penetration boundary condition, the first one is called the no slip boundary condition. So these two boundary conditions are one of the most important paradigms in solving fluid flow through channels and pipes, and they are extremely necessary in order to obtain an analytical solution. However, okay, so coming back to this equation, we know that we have boundary conditions and we have certain forces that would play a role. One of the forces is the body force or the pressure. So this pressure might originate from gravity or something like that. It might be electrical in origin, magnetic in origin, or something like that. So this is a force that operates on the bulk. The other force with which it competes is the viscous force. So any flow for that matter, be it flow of blood in your capillaries, flow of water in pipes, flow of medicine, transport of water in a single cell species, or transport of water in a huge tree. All of these processes basically.
Okay, yeah. Go ahead.
Okay. So all these forces, all the flow basically happens due to a competition between these two forces: the body force, which operates on the bulk, and the viscous force that operates across the surface. At least that is how it is calculated. And this balance is maintained by these two conditions: the no slip and the no penetration. So this is how fluid mechanics has evolved for over the years, and this was pretty much there, and this is the pretty much thing that you read in all textbook of fluid mechanics. However, in 1971, there was a paper in Journal of Colloidal Interface and Science, which tried to do a small mathematical interpretation of this momentum transport equation for a droplet moving on a surface. So the droplet can move because of numerous reasons. So it might move because of a body force, because of electrical force, or simply because of the virtue of evaporation. So if the droplet is evaporating, you understand that it is going to shrink, and maybe after some times it would become something like this. So what they basically did is that they tried to consider an infinitesimal element on one of the side and assume that it is a wedge-shaped element. Now, this wedge-shaped element, if it is placed on a surface and that surface is given a velocity u, by no-slip condition, which states that the fluid element next to the surface has to have the same velocity as the solid element, we would be also assuming that when the surface is moving with a velocity u, the fluid element is also moving with the same velocity u. So, in order to solve the velocity, obtain the velocity gradient, we know that velocity at, so let us assume this is capital U. So velocity of this fluid element here would be capital U. And if the height is a function of x, because it is changing, it is a wedge, it is a triangle. So it is a function of x being the coordinate in this direction. So the gradient of the velocity is given by u by hx. Now, and by Newton's law, you understand that the shear stress would be given as the multiplication of the viscosity of the fluid and the velocity gradient. And so similarly, the energy of the surface would be given by viscosity times square of this, because force multiplied by u dot would give you the energy of the surface. And now I try to integrate it. So what I would get log of h naught by h integrated over 0 to L, and hence I get a infinite shear stress at the wall. Without going into the mathematics, if I say that the contact line is, just understanding it from the physical argument, the fluid element next to the solid element is not moving, hence the contact line can never go from the point 1 to point 2, because fluid element next to a stationary surface doesn't move. So making this situation an impossible thing. And hence they coined this term, not even Hercules. Hercules is the Roman equivalent of Hercules. So not even Hercules could sink a solid, and rhyming with it, they did not even Helios, that is sun, can evaporate a drop of liquid, because motion of contact angle has been rendered impossible by our good old physical model, which states that there is no slip and no penetration. Hence, at this point, sorry, I was supposed to do the scribbling on this slide, I did it on this. That's right. Okay, so not an issue. So at this point, we question, so what is the validity of no slip boundary condition? So it is very simple. The person who did the Navier-Stokes equation, the momentum balance equation, Navier himself postulated something. See, Navier was a mathematician. For mathematician, physics doesn't matter. If you are an engineer, for you, the quantity infinity should be quantified. The quantity infinitesimal should also be quantified. For example, if you are standing, you are a civil engineer and you are standing in a building, another building at an infinite distance would mean probably a few hundred meters. On the other hand, if you are a process engineer who is doing something related to transport of drugs, for you, 2 channels of chemicals at infinite distance would be a few meters. If you are a biologist, for you the infinite distance might be few centimeters or millimeters. So, but for mathematician, infinity is infinity, zero is zero. So Navier did assume something which is called the slip boundary condition, which was which states that fluid elements next to the solid surface can have a finite velocity, and that us can be given in terms of something called the slip length, which we would come and explain it to you in a short while. So Navier gave this equation. So we immediately, if this is something unrealistic, contact line is moving, then contact line is obviously slipping. And we have a mathematically defined different equation for taking care of it. But the problem is that we need to take into account what would be the forces that would be playing a role here. So instead of the regular channel flow that we take, let us try to assume what happens if flow through a channel is occurring via capillarity. So by your basic knowledge, you know that the meniscus of a capillary would look like this, convex upward. So fluid moving this side, and it is it looks like this. So gradually it is filling. Now the force that would be aiding the motion of fluid in the channel, that would be the capillary force or the surface tension force. So again, so what do, you try to take the components. So one of the components would be in this direction, that is the cos theta component. So if T is your surface tension, you do T cos theta, multiply with the perimeter, you get the component that is acting in this direction. The other component, that is the sin theta component, would be acting along the periphery outwards and would cancel each other. This would be opposing again our good old viscous force, and the balance of these forces would give us the equation of this. But if this contact line is supposed to move or slip along the surface, what is the force that is triggering this motion? So that becomes the important question, because you understand this surface tension and viscosity, they are bulk measurement of forces. For a balance of force at the contact line, we do not have any tool. So as an option, we try to go back in history and try to see how the evolution of forces have been observed. And here I copy paste this diagram because I love this diagram when I saw it as a kid, and I don't know, it looks pretty weird, but this diagram basically shows three people, Archimedes, Galileo, and Newton, respectively discovering their doing their most famous experiments, quote unquote. So Newton finding out gravitation, Galileo showing that viscous resistance doesn't matter, and Archimedes having his Eureka moment. Now, like to link these are three of the most important discoveries about the forces of nature, and give or take, they are mostly talking about gravity. So Archimedes, a long time back, so all of you know that, he using the principle of buoyancy, he discovered the principle of buoyancy and calculated that when a body is immersed in water, a buoyant force acts on the body, which is equal to the weight of the volume of the displaced liquid of the body. So basically, what he was saying was force of gravity of the fluid and the liquid acting in of the fluid and the solid acting in different directions So a summation of gravitational force giving the net gravitational attraction to the body which has been immersed. Galileo again, he had two balls of different sizes and showed that they would reach the ground on the sun at the same time. Again, postulated the role of gravity, and finally Newton laying down the property of gravity in terms of concrete mathematical evidences. And now gravity is basically the role, the force that would guide all these major forces of nature. So apart from gravity, there are typically three other major forces that operate in nature. One of them is the electromagnetic force. The other is and the other two are the strong and weak forces. So on a scale that is of our size of human body, mostly we would feel the forces of gravity. But as we go down, electromagnetic forces and the strong and weak forces, especially at the molecular scales, they become very important. Now historically, after Newton has postulated the laws of gravity, forces were pretty much measured and their equations were laid down very clearly. However, this scaling down to level of particles was not very clear. And around Newton, there was another scientist, Robert Boyle, who postulated a law, and that came into direct conflict with the Newtonian mechanics. So you know the Boyle's law? Boyle's law is basically PV equal to constant. So if pressure is increased, the volume decreases, and if pressure is decreased, the volume increases. So which meant that if particles are brought closer to each other, they tend to exert greater force on the walls of the container, which is something that is not the classical theory of Newton, because Newton gave that two bodies would attract each other, and he also gave an equation, and that equation pretty much worked. It pretty much solved everything that Copernicus and Galileo has said. So this was something which was very much conflicting. So, and at that time, you understand, people did not know the nature of molecules and atoms, not very even sure about their existence. And hence, Boyle's law was something that could not be clubbed together with the Newton's law of gravitation or Newton's laws of motion. Then again, around, so you know this guy? He is Benjamin Franklin, one of the founding fathers of USA. And I could have written his lifespan in the slide. I forgot. But anyway, you know that he was most active during 1776, the year USA got independence. And prior to 1776, he was a British by ethnicity. So, and apart from his political affiliation, he was also a scientist. And he was a member of the Royal Society. And obviously, beyond 1776, I don't know how much he was welcome in the Royal Society, given that he has revolted against the Britishers. But in 1774, he presented a finding in the Royal Society, an experiment which is not as popular as the kite experiment you see here. So, hence this was the image that I could get from the internet, not the other one. So, there is this pond, Clapham Pond, in London, in UK. So, what he used to do, so these guys were very rich, okay. So, they were rich in USA, they were rich in UK, so they were always rich. So, he used to go on this boating, and he used to have this, obviously, picnicky type of thing. So, he used to carry food and olive oil and stuff. So, and playfully, he used to pour 1 teaspoonful of olive oil into the water. And he used to observe something that has been observed for ages, and you also have observed. oil tends to spread on water and would steal the wave. So if you have ever seen a water body, there are always ripples on the water body. If you put a little oil on it, the ripples around that region where the oil spill occurs are removed. So it sort of irons out those ripples. So he used to observe that, and the moment he pours that olive oil, he would see always the area was quarter of an acre. He repeated the experiment in different conditions, and he always observed that. Now he reported this observation in the Royal Society meeting, and nobody thought of doing a small mathematics with it. What is that mathematics? The volume of olive oil in 1 teaspoon is about 1 centimeter square. A quarter of an acre is 1000 meter cube. Divide the volume by area, you would get about 10 to the power minus 9 meter. And what is that? That is the dimension of a molecule, give or take. So basically what was happening? The moment you drop olive oil, it is spreading itself on the entire surface, and you are getting a monomolecular layer. So what Benjamin Franklin found out in 1774 was the dimension of a molecule. And but for at least about 100 years, no one did this calculation, and no one had the idea of a molecule. After about 100 years, these people tried to see what is the structure and dimension of a molecule. Thomas Young, who is also known for the Young's equation, first came up with the size of a molecule or a particle. Rod Rayleigh, he did that division and showed that, okay, 100 years back, what Benjamin Franklin observed was actually a single molecular layer, and Laplace proposed that molecules of similar type stick to each other by a property called cohesion, and molecules of different type stick to each other by a property of adhesion. And he gave obviously the Laplace law. And these people mostly constructed the concept of surface tension, and that is where we started moving towards. So there was a parallel development. We are also trying to observe so Dalton came along, and we know that molecules and atoms are things, they exist. What are the particles? And these people also tried to see what are the upscale manifestations of existence of molecules and atoms, and how do they affect the behavior of flow under different behavior of fluids under different conditions. So that is how it evolved, and from that, let us go back and revisit the paradox of the paper. So in order to resolve this paradox, in order to find out what is the boundary condition at the three-phase contact line, we have to find out what is the molecular model of the contact line. Because any continuum model is insufficient to predict the dynamics of a contact line. Our continuum models, or the models that are given by the partial differential equations, well-known things of calculus, they are good for a bulk fluid, they are good for motion of capillary. But when at the interface, we are transiting from the fluid phase to the liquid phase, we are stuck at a point where the boundary conditions cannot be given. So we are stuck at a point where Benjamin Franklin was stuck, while he could not calculate the thickness of a monomolecular layer. And hence, in order to understand this, we have to resort to molecular models, which the typical Poisson flow equation, Navier-Stokes equations do not take into account. They do not take into account the properties of the fluid at the interface, the different sorts of roughness and structure. So to model this, we need to take into molecular rate. So now at this point, let us quickly go and formally explain to you the concept of weightability. So the common perception of weighting and non-weighting is the amount of spread that a droplet would have on a surface. So as you can see on the left hand side, it is a surface which is non-weighting. So you can assume that this is the surface of your car, which is supposed to not get wet, because a wetted surface, if it gets wet with raindrops, you are going to have a lot of problem. There will be erosion and stuff. And also modern day lenses come with a coating. The glass lens, they come with a coating so that droplets do not stick to it. The other thing here that you see is a particle where is a surface where water has formed a film and it has spread. As a result, this has wetted the entire surface. Also, some common observations are that a regular glass surface is wetted by water. So when you put a droplet of water, it tends to form a film on a glass surface. Mercury, on the other hand, would not wet glass. So it would start forming small sphere, and if you try to spread it over, it would break itself into smaller spheres, but it would never form a film. So, and since water is the most common fluid, wetting surface is usually called a hydrophilic surface. And obviously, if it is not water, then there are other terms like lyophilic. Non-wetting surface is called a hydrophobic surface. So that is the common concept of wetting. And with this concept, and obviously contact line, we would come to these applications later. Associated with wetting is the concept of contact angle, which is basically given by the angle subtended within the fluid by the fluid vapor interface on the side of the solid. So as we know that the different interfacial tensions act at the interface, the solid vapor interfacial tension acting outwards, the liquid vapor interfacial tension acting along the surface of the solid, and the solid liquid interfacial tension acting within the fluid. A combination of this is given by the Young-Duclos equation, or more commonly called the Young's equation, and this cos theta is the contact angle. So traditionally what we have, when a surface is wetting in nature, then this contact angle is acute. If a surface is completely wetting, it forms a film and it is impossible to measure the contact angle, and by default it is considered to be at 0 degrees. If the surface is non-wetting, the contact angle is greater than 90 degrees. So for water, the standard is an acute contact angle would mean the surface is hydrophilic. An obtuse contact angle would mean the surface is hydrophobic. Now, the value 90 degree at which we consider a transition is a pure coincidence. So it happens that the term acute, obtuse, and the wetting properties, they somehow thermodynamics had made them to coincide with this 90 degree value, particularly for water. However, please do not stay complacent that a wetting and non-wetting behavior for any fluid would be transitioning at 90 degree. If it is alcohol, that value might be different. If it is a polymeric fluid, the value might be different. So this is a pure coincidence that at 90 degree for water the transition occurs. Okay, so this is the concept of weightability and contact angle, and starting here we switch our gears to the next part where we try to find out what is the microscopic signature of this weightability and contact angle, which we know by equations, rough equations in continuum, otherwise look like. Okay, so at molecular, to see the molecular picture, what we need to do, we need to go for a particle-based analysis. So instead of trying to look into the whole fluid interface, we try to take certain particles at the interface and try to see how do they evolve. So what we do, we take the wedge of Hu and Scriven and try to see if this is composed of certain particles, how these particles would be behaving given a particular set of conditions. Okay, so let us say this is glass and this is water. How my particles are going to behave if they are placed at the corner of the edge. So there are two approaches for it. The first approach is the statistical approach. So statistical approach comes from the random walk approach. So what do you have? You have a grid, say a one-dimensional grid. You stand at the center of the grid, and then there are two possibilities to jump in the next step. Either you can go forward, you can go backward. Similarly, if it is 2D, there are four possibilities for it. So let us take, without loss of generality, let us take it to be a 1D thing. So let us say you assign some weight that it is like a drunk person trying to walk back home. He doesn't have his orientation correct. He knows he is on a road. He might be taking 2 steps forward, 3 steps backward. So my molecule is in a similar state. I assign some weight. So say at time t equal to 2, it might be here. Then again, at that time, I have 2 spots for it. Time t equal to 3, it might be coming back here. Again, 2 spots, and so on and so forth. Now, if there are multiple molecules, obviously there is another probability of collision. When a collision occurs, you have to again assign it something and calculate it similarly. So those calculations are called the Monte Carlo simulations, which are statistical in nature. So they assign a probability and try to find out how my contact line is going to evolve as time passes. The other solution is deterministic in nature. So what the deterministic solution would do? It would try to find out what is the force that is acting on this one. Okay, so a deterministic algorithm would try to find out what is the force that would be acting on this molecule sitting on the edge. And I know that this molecule sitting on the edge is interacting with the molecules that are behind it in the liquid, that are here in the gaseous state, that are here in the solid state. So I try to find out what is the force that is acting on it. So I try to sum up all those forces of electronic origin, and you know that each particle would have some charge, and a sum of those forces would give me the acceleration, velocity, and the position of the particles as I try to integrate it. And that way of doing a deterministic simulation or deterministic calculation is done by molecular dynamics simulations. And so in order to understand the concept of weightability and contact angle, we resort to similar such simulations. So to understand what are the forces, so we have understood gravity and electrostatic forces in great detail, but at molecular scale, where our rules of calculus no longer applies, we try to go back and analyze what are the forces that are important at those scales. So this is what I was just mentioning to you. So this is the basic algorithm that it does. So it tries to calculate the force that is acting on a particle and then integrates it. Mass times acceleration is force, that is from Newton's second law. We integrate it to obtain velocity, we integrate it to obtain the position. So that is how we try to find out how a particle is evolving. And so always doing calculation in terms of force is not possible, so we try to do this calculation sometimes in terms of energy. And that energy is given in terms of force. So this is something that is that would be of interest. So we know that two particles, so Newton said that always two particles would be attracting each other. Boyle's law and the discovery of molecules and their electronic cloud and the structure of a nucleus which is inherently positive surrounded by negative electrons gave us the concept that there can be always a force of repulsion as well along with the attraction. So how do I model interaction between two particles? So the initial interaction models that came into, so basically when I am doing a deterministic, so if I go back to this diagram, if I am doing a deterministic thing and I want to calculate the force field of this particle, I need to model the interaction with the particle that is here, and let us say a square particle means a solid particle. So what is the interaction here? So how this interaction is being modeled? So very initially, when people did not have sufficient computational tools or sufficient understanding of the molecular structure, they did model molecules as hard sphere models. So very similar to interaction between, say, two tennis balls or two deuce balls. So what it is like, when they are at infinite distance, force of gravitation or some unknown forces is acting in an attractive fashion, and they might come close to each other. But they are hard sphere, and there is no possibility that these spheres would overlap. So there is no chance of compression, and the moment these spheres, sorry, the overlap was, no, let me draw it properly. So this is the center. So the moment the distance between their center becomes equal to the diameter, they have hit each other and the repulsion goes to infinity. So this is the typical hard sphere model, and people started modeling the interaction energy based on distance on that. But with more and more knowledge about the electronic structure, people came to know that electrons are not actually particles spinning around particular orbits like planets, but it is more of a cloud in an orbital, and hence it is a probability that this accidental diagram now can be used, that these particles actually overlap. So their distance, interparticle distance, might come below the distance of the diameter of the particle, and hence we come up with something which is called the soft sphere model. So what happens? The moment they collide, there is no longer attraction, there is repulsive forces, but that repulsive force doesn't go to infinity. Rather, it steeply rises, and that steepness can be defined by a mathematical function, and more and more the particle becomes closer, it rises. Hence, so this is basically something trying to model the structure of electrons and nucleus. So basically when they are far apart, they are attracting each other because the nucleus of particle 1 is attracting the electrons of particle 2 and vice versa. When they have overlapped, the electronic cloud of particle 1 is repelling the electronic cloud of particle 2, and hence there is a repulsive force. Now, after a degree of overlapping, now the nucleus of particle 1 and particle 2 are interacting. So it's a concentrated positive charge repelling another concentrated positive charge. So now the repulsion would increase, and hence it is going to become more steeper and become more repulsive. So that is how pair potential evolved, and people had an understanding, okay, so if we are coming down from planetary objects in the orbits where force is only attraction, if we are coming down to molecular scale, we have to model it as a combination of attraction and repulsion. So And with these two initial models, several people did quantum mechanical experiments and tried to solve the Schrodinger's equation and come up with different solutions to this, and tried to project different equations. And from those pair potentials would have to take into account three major forces apart from the Coulombic forces or the electrostatic forces into account. So, see, Coulombic forces are, Sanket.
Yeah, so I had a question that so basically in the soft model that you are talking about, you claim that the force, that the repulsive force, I think it increases smoothly. So basically, can you explain a bit like what exactly you mean by like it's increases smoothly? I mean, is it a continuous function or is it? Yeah, so basically on that.
Yes, it is a continuous function. So basically, I go back. So you can see it is a r to the power some exponent, right? And what is that value of exponent? That we do not know. So that has to come from either experiments or EA. But we know that it is not going to infinity the moment the particles overlap. Rather, it is, this looks like an hyperbola. Hyperbola would be 1 by r, right? So, and the smoother it is, larger would be the value of n. So, if you have r to the power 6, probably it would look something like this. R to the power 12 would look something like this. Okay, obviously not touching this. And otherwise it is r to the power 0, goes straight up. So that is something that we have to figure, that people have to figure out when they try to do the pair potential thing.
Right, okay.
So, and yeah, in order to find out this value of exponent, apart from the Coulombic forces, that is electrostatic forces, people would have to take into account the forces of interaction which are typically present in molecular scales, and those are broadly classified as van der Waals interactions. And obviously you remember the van der Waals equation of gases, where the pressure and the volume terms are augmented. So similar to it, this van der Waals interactions can be classified into three interactions, which are the orientation force or the keystone interaction, induction force Debye interaction, dispersion force London interaction. So, so very quickly we know that when there are two charged particles, I give the interaction energy between these two particles as q square 4 pi epsilon naught r, right? The interaction energy. Force is obviously r square. So interaction energy for two fixed charges vary as 1 by r. Now, what the van der Waals concept of interaction states that? Firstly, the orientation force states that there is a fixed charge. So supposedly there is a sodium ion sitting in the system. The sodium ion is interacting with an uncharged system, forming a local dipole. Okay, so what is a dipole? Basically, the positive energy, the positive polarity of the sodium ion is pulling towards it the electronic cloud. So if this is the sodium ion sitting here, and this is, say, some neutral atom sitting here, what it does, it is trying to pull the electronic cloud here, making this negative, this positive. As a result, I have something called like the keystone interaction. And without going into the entire discussion, we say that the keystone interaction, it can be, so you know that the dipole interaction energy varies as 1 by r square. So when there is fixed charge and dipole, it would be varying as 1 by r cube. dy interaction is that when there is a dipole interacting with another induced dipole. And finally, dispersion interaction is when one of a local charge distribution in the system is interacting with another local charge distribution. So the system is as such neutral. So imagine it's methane, which is very well distributed, C with 4H in 4 directions. So the rotation of electronic clouds would cause a localized positive and negative charge in a region, and that would introduce a localized negative and positive charge in the other region. And by principle of induction, or if you have time you can calculate, this dispersion force would scale as 1 by r to the power 6. Okay, so actually I would share the presentation with you. Each of these forces have been derived here. Okay, so we know that somehow if I am to model the pair potential, I have to model the attractive forces as a function of 1 by r to the power 6. Okay, but there is also a repulsive force for which the modeling is not very easy, because everything has to be integrated with a negative sign. So a dipole is inducing another dipole, not attracting it but repelling it. So I have to do this entire thing by integrating it with a negative sign. So that becomes very complicated, and hence the energy variation of repulsive force is not very clear. So this guy, John Maynard Jones, what he did, in order to simplify the calculation, he said that repulsive interactions are far weaker than attractive interactions, and I need to do these calculations in a computer. My computer is not very strong. So since I have to calculate 1 by r to the power 6 at every step, let me model the repulsive interaction as a square of the attractive interaction and model it as 1 by r to the power 12. As a result, so these are the interactions parameters which you can see. As a result, something John Maynard Jones came up. So Maynard Jones is not two guys, but it is one single person, came up with a potential called the 612 potential, which looks like this. As two particles come closer from infinity, they tend to attract each other up to a certain points when their diameters collapse. Beyond that, the repulsion increases and increases rapidly beyond that, tending to a hard sphere model. So you can see how the combination of hard sphere and soft sphere model has been used, and by doing experiments and quantum mechanical experiments or solving Schrodinger's equation, you can find the these terms, the epsilon naught and sigma. Graphically, sigma is the distance, sigma Lennard-Jones is the distance where the interaction energy switches from negative to positive or attractive to repulsive. So that is the distance beyond which the interaction energy is repulsive. Epsilon here is the depth of the well, the maximum attractive interaction for which this occurs. Obviously, by differentiation and integration and stuff, you can find out that this distance is √2 times sigma, the distance at which the well occurs, and everything. So this is a very beautiful potential interaction which was proposed by John Maynard-Jones, and this is mostly used to model everything. And typically, every substance that exists in your chemistry laboratory on the face of the earth can be modeled in this way. And so using this, we can also model the contact line dynamics. Okay, so this is the entire history of these things, how you model each term and stuff. So skipping all this, So this is how a water molecule would look like if it was cartoonized. And so say Lennard-Jones potential was applied to water molecules, so that would give you the angle, you know, HOH angle, the thing in chemistry. Probably middle school chemistry asked you this question: what is the partial charge on oxygen atom? What is it? So this everything would come out from that interaction between two particles. Okay. So everywhere you do, this is how you, so you obtain the velocity, again a repetition of that, and you do it, and you then try to find out whether the interaction is between particle or particle surface. Is it adhesion or cohesion? How does it happen? So, and then we come back to our answering this question of infinite energy dissipation, or the question that would Hercules be able to move a contact line or sink a solid? So this is the Navier slip boundary condition we are talking about. Explain hydrophobic surfaces. So we would come to the applications at the end. So using this, we tried to delink the slip from weightability, or the contact angle from weightability. So on a surface, so I do not have much time, right? I have about 5 minutes to go, right, Sanket?
Yeah, if you want, you can go for more 10 minutes, I guess.
Okay, so I would take 10 minutes. So let me slow down a bit and explain this to you. So yeah, I was trying, initially I tried to explain you what is the slip boundary condition for a surface, and as you can see, typically the no slip condition would say that the velocity at the surface would be equal to would be equal to the velocity of the stationary surface, or zero. But mathematically, if I have a slip velocity, my boundary condition would look something like this, given by a slip length. So basically, I try to extrapolate my velocity profile and see where it goes to zero, and that length is given by the slip length. And the advantage of this is that nowadays we need maximum transport with minimum energy cost, because you see, to have the water supply in your tap, you need to use a pump to pump it to an overhead tank. So you are consuming electrical energy. So that is something very much taken. But there are several cases where we might not have that energy to drive a substance. So say certain medicines which would need to go and kill a cancerous or tumorous cell in our body. So we cannot put a battery in the medicine or that killer drug and inject in our body. Rather, we have to propose a mechanism where it can use energy from maybe the heat of the body or certain chemicals and perform the function. Similarly, certain medicines that needs to be transported, certain remote sensing functions. For example, I need to operate a video camera, wildlife video camera. I need to observe something in space. For that, I would need my flow to occur without drop in pressure. So, if I can somehow ensure that my slip length is very large, what I'm going to have that without application of pressure, simply by texturing the surface, I can ensure that my fluid flow can occur. So typically, what we do, we try to. So this is also something. So something very common. So in order to obtain minimum pressure drop, we try to smoothen the surface. We try to polish the surface, making it very, very smooth, so that frictional drop or frictional resistance or viscous resistance is least. However, that doesn't ensure that my flow would occur entirely for free, because there needs to be some additional pressure gradient that needs to be given. However, you know that the concept of capillarity, where capillary rise can occur directly via surface forces. So if you dip a glass bore in a beaker of water, water rises by force by simple capillary force. Similar to it, all these huge plants that we have, they also use this force of capillarity to have free transport of water. But there is a problem between these two conditions. If I want to have free surface driven transport, I need to make my surface hydrophilic, because if contact angle, my theta is not acute. So if you can recall that T cos theta, surface tension times cos theta, would not be positive. It would not be causing rise of water in the capillary. So if you know it's a non-wettable fluid, again high school knowledge, if you have a beaker of mercury and dip a glass bore in it, there will be depression, not capillary rise but depression. So in order to have surface driven transport, I need to have a hydrophilic surface. In order to have surface, in order to have greater throughput, I need to have greater slip. Now, this property of slip, fluid layer sliding, is connected to hydrophobicity. A non-wettable surface would not allow wetting of the surface and would be clean to slip. A wettable surface has capillarity but doesn't allow slip. So this is a concept that has been unified in history, and via molecular dynamic simulation, we try to propose a surface where these two concepts are dealing. So, so this has several use applications, which so I will share the slides with you. You can go through these applications. So one of the other thing is the self-cleaning surfaces, which is now very important. You would not want your mobile phone or your car window to be very sticky, because otherwise your fingerprints would stick on it. But that itself makes cleaning it very difficult, because if you put water in it, water is also not going to stick. So and gradually that causes the degradation that you see. Even if you so Lenskart is a very popular website which sells this glass eyeglasses, and they would usually put hydrophobic film for some 100 or 200 rupees. So you put that film and observe how fast your your eyeglasses degrade. It is the mere fact that the surface is non-sticky to water is making it more prone to scratches and dirt. So that is something. So so there are several applications. The agenda of our work was to arrive at a surface which can be wettable at times and non-wettable at times. And in order to do that, we tried to see how this slippage occurs on a surface. And that occurs by liquid water trying to skip from one lattice parameter to another lattice point. So you know every solid structure surface is given by a lattice structure, a BCC, FCC, or a simple cubic structure. And the way the contact line moves from one point to another would depend on the distance between two lattice points on the solid. So by using the interactions that we have talked about, we tried to do a Newton's second law of analysis of the entire fluid flow through these different solid surfaces. So what we did, we tried to vary this lattice parameter length. So it is nothing but you try to have like a mold and put certain particles at a certain place and generate the surface. So it is like something that you do with wax or say a clay type of thing. So you generate a surface at particular distance, and as you change that parameter, you observe that your slip value decreases as those lattice points move further away from each other. So this, so we would explain this at the end. So Similar to this, we can add a little salt to that to find out, to obtain a surface which has artificial pinning zones. So water gets an opportunity to slip on artificial locations, and hence our slip length decreases by increase of concentration. And what we do is, via a combination of wettability and slip, wettability and surface parameter, we try to arrive at a point where even for a surface where contact angle is very high, we have obtained state. So what is this basically we are trying to do? So these graphs are not interesting, so rather this is interesting. So this is like, so in West Bengal, kids play a game called Kumidanga. So the rule of the game, so I'm running out of time, but allow me 2 minutes to explain the rule of the game. So so you find out a person who is basically, this is like basically chore police. So there are certain demarcated zones which are called land. So, and one of the kids disguising as crocodile would be staying in water, and the other kids would need to jump from one landmass to another landmass without getting interrupted by this crocodile or the kid who is pretending to be the crocodile. So when you have more land masses, so whoever has played this game would know this is true. When you have more land masses and a single crocodile sitting there, it is easier to skip the land masses. On the other hand, if you have more people, more kids disguising as crocodile trying to catch you, it would be very difficult to swap between the land masses because there is a more probability to getting caught by one of the crocodiles. So this is what happened when you are trying to put these salt particles in it. So they are providing artificial pinning pinning zones where my slip length is decreasing. Now, in a case where there are huge number of kids trying to swap the islands, huge number of kids disguising as crocodile, jumping between slots becoming impossible. Because all the slots are filled, all the islands are filled, the water is completely filled with crocodile, and there is no probability to jump, hence we get an absolute stick. So application wise, if we can, so this surface can be generated. If we can generate, we have generated this surface. So just by tuning the solute concentration and structure of the surface, we have a surface which, when needed, can act as a sticky surface, allowing transport of water, allowing cleaning it, and such stuff easier. And when I'm operating the surface, I can just tune the salt concentration, making the surface non-wettable again, making the flow easier. So yeah, all those theories are here, but the interesting part is over. So yeah, thank you for your attention. Please feel free to ask any questions.
Yeah, thank you, Professor Bakli, for delivering a so interesting talk. Yeah, it was a really nice talk based on we covered a lot of stuff from a historic point of view and coming to a scientific point of view as well. So if people have any questions, they can ask now. They may unmute themselves and ask now. Okay, so if no one have any questions, then actually I had a question. So you were talking about two simulations. One was Monte Carlo simulation and another was molecular dynamics simulation, right?
Yes.
So I'm not sure if this is the right question to ask, but so basically you might have two things that like in Monte Carlo simulation, you might have a set of algorithms through which you do the calculations, and also in molecular dynamics simulation, you have the same type of stuff. So basically, in terms of time complexity, which simulation is faster?
Monte Carlo simulation is much faster.
Okay.
Because see, in molecular dynamics, at every step you are calculating the energy of the field, differentiating it, obtaining force, then integrating it, obtaining velocity, then position, reassigning the position, and then repeating the whole process. In Monte Carlo, you just assign a new position, repeat. Assign a new position, repeat. So it is just one step, and molecular dynamics is 5 steps. So molecular dynamics is almost 100 times lower than Monte Carlo.
Okay. Okay. Thank you. So, okay. So we have a question in the chat box. So Suvam Maiti asked if, like, what is the scope in research of this weightability and stuff? So can you please describe a bit?
Yes, Shubham. Yeah, that is a very nice question. Actually, it has a lot of scope. So, nowadays it is all about generating smart materials, smart interfaces, smart surfaces. So, starting from defense to energy applications to biological applications, everywhere you would have to tune your surfaces accordingly. So, it is no longer like so you need a fluid flow, you put a tube or pipe and obtain fluid flow. Everywhere you would have to design a smarter interface and it has to be tuned according to the application. So the scope of research is pretty huge, and this is a very nascent area. So say for example, this COVID pandemic, you see a lot of research is going on. How does the virus travels through cough droplets? So that is also fluid droplets traveling across interfaces, and the solute, which is the virus in this case, we have to restrain its motion so that it doesn't enter our system. So there is a huge scope, and yeah, if that was your question regarding the scope, and obviously if you have, this is a short answer that I gave. If you have any detailed question, you do have my email ID and contact, you can contact me.
Okay, so does anyone have any other questions?
Good evening, Dr. Bakli. Myself, Dr. Kamlesh. I am a faculty coordinator of IIChE here. So it was wonderful listening to you, and you have given an excellent presentation. Your very interactive slides you have presented, and it's a very well. It's a new area for our students to think and explore, where they can work, and many things they have to learn actually, and it's a good area, and it's very difficult to get everything in this such a small span of time. Yes. And because of the huge work you have done in, I have seen your presentation, your publications in this particular work. So you have presented it in a very simplified manner. So that's the wonderful thing about it. And
basically, yeah, so thank you, Professor Bakli, once again for accepting our invitation and delivering a talk on Saturday evening, which is generally a holiday for everyone. So yeah, it was really wonderful to have you, and we hope to have you once again sometime in the future. Yeah.
Thank you for turning up on a Saturday.
Yeah, right. Yeah. So yeah, thank you.
So it's our pleasure. It's our pleasure to listen to you, Professor.
Thank you. Thank you.
Thank you for sparing your valuable time. Thank you.
Yeah. So yeah. So thank you very much once again. So yeah. So kindly share your presentation with me. I can share with it.
Yeah, sure.
With everyone. Yeah.
Sure. Okay. And you can share my email ID with.
Yeah. Sure. I will do that.
If they have any doubt, they can directly mail me.
Yeah. Sure. Okay.
Thank you.
Okay. Okay. So we can end now, I guess. Yeah. Okay.